This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to the discussion. Today we're delving into a research paper titled Competency-Aware Planning for Probabilistically Safe Navigation Under Perception Uncertainty. This paper tackles a critical challenge in autonomous navigation: how to ensure safety and efficiency when the perception system, often a deep neural network, is uncertain about its predictions. Let's start with the core problem. What are the limitations of traditional depth-based navigation systems in complex terrains, and why are learning-based components becoming increasingly necessary?
Traditional depth-based navigation struggles in unstructured environments lacking clear paths or landmarks. The inherent limitations of relying solely on depth data become apparent in complex terrains with unpredictable obstacles or varying surface conditions. Learning-based perception models, particularly deep neural networks, DNNs, offer a more robust solution by analyzing terrain traversability and enabling more effective navigation. However, these DNNs introduce their own set of challenges.
Indeed. The paper highlights the inherent limitations of DNN-based perception models. Can you elaborate on these limitations and why they pose a safety risk for unmanned ground vehicles, UGVs?
DNNs are black boxes, lacking transparency and explainability. They can be overconfident in their predictions, especially when encountering data outside their training distribution, out of distribution or O data. This overconfidence, coupled with their sensitivity to data distribution shifts, can lead to surprising and potentially catastrophic failures with little warning, posing significant safety risks for UGVs.
So the paper proposes a competency-aware framework to address these limitations. What is the core idea behind this framework, and how does it differ from existing uncertainty-aware navigation schemes?
The core idea is to estimate the perception model's competency, its confidence in its predictions, both globally for the entire image and regionally for specific image segments. Existing schemes often rely on uncertainty quantification methods that don't handle OD data well or provide only binary anomaly decisions. Our framework provides a probabilistic competency score, allowing for probabilistically safe control schemes that maintain performance under various uncertainties.
The paper introduces a probabilistic and reconstruction-based competency estimation, PREE method. Can you explain the mechanics of this method, focusing on how it estimates both overall and regional competency?
PRECE uses a reconstruction-based approach. For overall competency, an autoencoder reconstructs the input image. The reconstruction loss, compared to a distribution learned from in-distribution training data, estimates the probability that the input is in distribution. This probability, combined with the perception model's prediction probability, yields the overall competency score. Regional competency extends this by using an image in-painting model to reconstruct missing segments, providing a competency score for each segmented region.
How does parse distinguish between correctly classified in distribution ID samples, misclassified ID samples, and out-of-distribution ED samples? What about the regional competency maps? What are the key performance indicators used to evaluate the effectiveness of parse?
ParseCity effectively separates these sample types. Correctly classified ID samples receive competency scores near 1.0, OD samples receive scores below 0.3, and misclassified ID samples fall between. Regional competency maps similarly distinguish between familiar and unfamiliar regions. Evaluation uses metrics like the Kolmogorov-Smirnov KS test, area under the receiver operating characteristic curve, AUROC, and false positive rate, FPR, to assess the ability to distinguish between different sample types and regions. Comparisons are made against existing uncertainty quantification and anomaly detection methods.
The paper then integrates these competency estimates into a planning and control scheme. Can describe the different competency-aware planners and how they utilize the overall and regional competency information.
The paper explores several planners. Some use only overall competency, resorting to safe actions, backing up and turning, when competency is low. Others use regional competency, avoiding low competency regions. The most sophisticated planners use both overall and regional information, selecting trajectories with high minimum competency along the path. An LQR controller tracks the planned path.
The paper evaluates these planners in a simulated linear environment with unfamiliar obstacles. What were the key findings regarding the impact of competency awareness on navigation performance? What metrics were used to assess performance?
The results demonstrate the significant benefit of competency awareness. The baseline controller without competency awareness had a high collision rate. Adding overall competency awareness reduced collisions but increased navigation time. Using regional competency information significantly improved success rates while maintaining low collision rates. Trajectory-based planners, leveraging both overall and regional information, achieved the best performance, demonstrating the value of regional information for efficient navigation. Metrics included success rate, timeout rate, collision rate, navigation time, and path length.
The paper mentions some limitations and avenues for future work. What are some of the key limitations of the current approach, and what are the promising directions for future research?
Limitations include the limited field of view of the camera and the lack of visual memory. The vehicle cannot see or remember previously assessed regions, leading to potential collisions. Improvements to the competency estimators are also needed. Future work includes developing a more general competency framework, extending the approach to tasks beyond classification, developing a global competency-aware planner, and incorporating safe exploration strategies to learn from unfamiliar regions rather than simply avoiding them.
This discussion has highlighted the importance of integrating predictive uncertainty into autonomous navigation systems. The PRCE method and the competency-aware planning framework offer a promising approach to improving the safety and efficiency of UGVs in complex and uncertain environments. Thank you for this insightful discussion.